So ladies and gentlemen, we have a great pleasure today having Professor Mikhail Glazov here, who is not only the corresponding member of Russian Academy of Science and leading scientist at the Yofa Institute. He is also a member of the International Advisory Board of the Abrikosov Center for Theoretical Physics. And Misha is an expert in symmetry effects in crystals and two-dimensional semiconductors, spintronics, and many other things, polaritons as well. And today he is going to tell us something about the transport of excitons in two-dimensional heterostructures.
Thank you very much. Thank you, Alexei, for inviting and presenting me. It's a great pleasure to be here. I will probably close the door. With acoustics. So indeed, I'm going to talk about transport of excitons in two-dimensional semiconductors, and we all know that these systems are now very actively studied, both experimentally and theoretically, and there are a lot of progress in the field. So in my talk, in my kind of lecture, I would like to speak about something which at first may look a little bit controversial, because when we speak about excitons, we typically speak about optical properties, about absorption, reflection, or transmission, about fine structure, and so on. But I want to tell you that sometimes optics can give us a hint, can give us a clue to the transport properties, to the way how quasi-particles propagate in these two-dimensional systems. Okay. So I do not want to spend a lot of time speaking about the material systems. I'm interested mainly in this talk. But still, I want to say that we are going to focus on these two-dimensional transition metals chalcogenides, the main representatives being the molybdenum disulfide, the selenide, and some other materials. And these materials are now called something like two-dimensional materials beyond graphene. These systems are direct band gap semiconductors with strong Coulomb interactions, and their optical properties are indeed dominated by excitons, bound electron-hole pairs. And in these materials, just due to the translational symmetry, one can expect that these excitons, these neutral excitations, can propagate in the plane of the system. Huge binding energy of excitons. So typically the binding energy of the ground exciton state is hundreds of milli-electron volts or more. Make these quasi-particles quite robust. So you can study exciton physics and even exciton transport at the room temperature. We can see that you can play some tricks with it. So very simple situation. At first, I will not need any details about band structure and so on and so forth. So let us just consider that we have a plane and we have a neutral quasi-particle, this exciton, which can be excited by light and which can emit light and which can propagate in the plane of our structure. And indeed, in this case, one can try to study transport. I will speak about theory, of course, but I will try to illustrate our theoretical results with some experimental facts. And that is why I want to show you some first experimental works where the exciton transport in these materials has been detected, and probably give you a little bit of information how one can indeed measure exciton transport. So people make quite simple experiment, quite simple optical experiment. They excite sample at some point with light, with a pulse of light, and then they measure emission of light as a function of time and coordinate. And in this way, you can imagine that if you created an exciton somewhere, then this exciton can indeed move into the plane, and then it can emit photon, so then you can detect the photoluminescence. And if you do it with space and time resolution, then you can learn how these excitons propagate. And this is what people typically observe. So this is a kind of coordinate result with within several microns range. And time result, spectrum of these excitons. So if you look at the experimental data like this, so nothing happens. Looks like the excitons simply decay. But if you normalize this distribution by the maximum intensity, so you just disregard the fact that excitons have a finite lifetime and die at some point, then you can clearly see that the distribution becomes wider in the course of time. what you can do, you can, for instance, compare the distribution at 0 delay, right after the optical pulse, at some time delay, say 400 picoseconds. It's indeed broader. And you can plot the squared width of this distribution as a function of time. So depending on some parameters, I don't want to go into much detail, but you can see that this squared displacement, this squared width as a function of time increases and increases linearly. And that is a signature of diffusive propagation. So if your quasi-particles were ballistic, then of course the distance would be proportional to the time, and the square distance would be proportional to the square of time. Here, the square distance is proportional to the first power of time, meaning that actually exciton doesn't move along the straight line, but moves along some kind of wiggly trajectory. So it diffuses. So my main goal here in this transparency was to show that indeed optics provides an access to exciton transport phenomenon, that one indeed observes exciton diffusion. We will speak about mechanisms of diffusion a bit later. And then, of course, it opens up a lot of possibilities to study different effects. I don't know, I have listed some of them: normal diffusion, nonlinear diffusion, formation of excitonic halos, quantum transport, and so on. So a lot of things people can do, more or less, with optics. Typically, when you study transport in electronic systems, you apply electric field, you measure the current, you get the conductivity, and then you study the dependence of conductivity on some external parameters. Here, we cannot measure the conductivities, excitons and neutral, but you can just observe their propagation in the plane of the sun.
Misha,
Yes?
something. So Glazov studied exciton diffusion in double quantum wells, and one of the effects that they faced was the limitation of diffusion length by lifetime for bright excitons, and of course much longer propagation of dark excitons. So in your system, will this be present or important?
It is very important, indeed. Bright excitons have a lifetime of several picoseconds. So even if you take into account all the states beyond the radiative cone, it would be, I don't know, 10, 20 picoseconds for reasonable temperature. So in fact, what people observe here is the dark exciton diffusion. In this case, lifetimes are long, but there are different mechanisms how dark excitons can be converted to bright. Small violation of symmetry and change of the selection rules. Also, sometimes people observe phonon side length in diffusion and high quality samples. I will probably show you once the spectrum. There are narrow phonon side lengths of dark excitonic states, and then you can measure the diffusion. You see here, for instance, the time scales are on the order of nanoseconds. And this, okay. Also, you can go to the room temperature. Actually, this particular plot from this paper is the measurement of exciton diffusion at the room temperature. And in this case, lifetimes are typically longer because bright and dark states are intermixed, and then in reasonable quality samples, the lifetime is on the order of hundreds of picoseconds. So indeed, there are. Sorry?
May I also interrupt you one more question?
Sure.
You plot here mean square displacement. What about tails of the distribution? Is it indeed as diffusion predicts, or you have stronger tails than diffusion will tell you due to longer hops and things like that?
Thank you for this point. Well, you can see here in this panel, I hope that you can see the pointer.
Yeah.
The points are experimental data, and then there are the Gaussian fits, which more or less I expected for diffusion. Unfortunately, the studies of the tail, as far as I understand, are kind of beyond experimental accuracy.
Okay.
So I will try to prove that, at least in high quality sample, this is a kind of diffusion related to free propagation of excitons and scattering by phonons. So it is not hopping between localized states. But there are some other samples, I'm not going to talk about it right now. Indeed, excitons are localized. And in this case, one can observe something like even sublinear expansion of this bit. which can be a signature of some returns and things like that. I'm not sure whether I have answered your question.
No, completely. Thank you.
Okay. So let us move on. Yeah.
To clear things, screens often.
There are different dark states. So one of the dark states in these materials are indeed the states, then the spins in the conduction band and the valence band are opposite, and then the recombination is forbidden. But in principle, there would be other states, because you can have electron in the K wave and unoccupied state in the valence band in the other K prime wave. And then you need a phonon with large wave vector to recombine, even if the spins are okay. So these excitons are also dark, and in principle, under experimental conditions with the experimental accuracy, they all propagate basically with the same diffusion coefficient. This is something I want to show and to provide also kind of link with previous works on bulk semiconductors and quantum wells. The exciton diffusion has been studied. So this is something related to nonlinearities. So of course, when people start observing exciton diffusion, they were interested in using some knobs to manipulate the diffusion coefficient. And here the situation is not that preferable as compared to electrons. So in the case of electrons, we have a very strong tool, application of magnetic field. And typically it gives a lot of information about transport. Here, unfortunately, we do not have magnetic field, or even if we apply magnetic field to the excitons, the effects are minor. You can induce some small spin splitting, but typically it plays no role. And of course, the orbital effects of magnetic field are also strongly suppressed, just because exciton is on average neutral. So there are basically two parameters you can play with. You can play with the temperature, and this would be the main part of my talk, but you also can play with the excitation density. You can try to put more and more excitons in the system. And this is something our colleagues have tried already 4 or 5 years ago in the group of Alexei Chernikov, then in Regensburg, now in Dresden. So they studied the exciton diffusion as a function of excitation density. Here on the right panel, I will probably use a pointer, several profiles of exciton densities for low excitation power, moderate excitation power, and high excitation power are shown. So basically, two effects are clear. First of all, with increasing the excitation power, the distribution of excitons becomes much broader. And if you just evaluate somehow the effective diffusion coefficient from the expansion rate, you basically get significant, by almost 2 orders of magnitude, increase of the diffusion coefficient with increasing the exciton density in the pulse. But also at rather high excitonic densities, you can see that the distribution is now definitely non-Gaussian, and there is even a dip in the middle. So in the point that you shine the light, for some reason, the intensity is smaller, and there is a kind of ring or halo which forms while excitons propagate. And then we studied these effects in a very simple model. It's kind of nonlinear diffusion, and nonlinearities, of course, arise from interactions. And there are 2 types of interactions in the system.
So, Misha, may I interrupt, but you consider no drift, right?
I will say about drift a few words a little bit later.
Because sometimes people believe that there is a pulsion from the reservoir and that provides a
Okay, this gives you a table. So if you want to speak about this formation of rings, indeed, there are 2 key mechanisms which were identified. One is the phonon wind. You indeed shine a lot of light on the sample, you hit the sample, and then there are non-equilibrium phonons which propagate out of excitation spot, and these phonons drag excitons. So indeed, it is like the force field. Also, there could be a Seebeck effect because there is an inhomogeneity in the exciton temperature, and it also provides a kind of repulsive force. The point is that at least for one monolayer, the exciton-exciton repulsion is quite weak. It is described by this blue term in the semi-phenomenological diffusion coefficient, non-linear term. You can see here this density multiplied by the gradient of density, and then here U naught is the interaction constant. So in principle, one can take this term into account, but at least in the experimental condition I'm talking about, for one monolayer, this term is quite negligible. The situation is very different if you go to bilayers, because in bilayers, excitons are dipoles, and then this constant U naught increases by 2 orders of magnitude, and then you can start seeing the same effects as people observed in quantum wells. Here, this blue term is not very important. What is important is the non-radiative recombination or AG term, which is given by this some coefficient Ra times squared density. What happens in these particular materials, kind of miracle, a sort of resonant Auger process can happen. You have two excitons, they interact via the Coulomb interaction, of course. Then one exciton non-radiatively recombines, and another exciton gets excited to some higher conduction band. The electron gets excited to some other conduction band, and there is a sort of resonance in this process just because of the specifics of band structure. So this coefficient turns out to be sufficiently high, much higher than in conventional semiconductors.
But it seems contradictory, because we just mentioned that exciton interaction is weak, and Auger relies on.
Okay, you are right that it may look as a kind of contradiction. So one thing is just repulsion of excitons. Like we studied, for instance, for excitons in microcavities, the exchange interaction between electron and hole. And this constant is U naught in some units, and it is relatively small. It is basically because this interaction constant. I understand that no one can see it in Zoom, but the estimated response square charge effective the electric constant, and then in proper dimensions multiplied by the order.
You can write in this.
Okay, I can try to write it here. Maybe it's
Some line. Yes.
E squared the electric constant, so it would be the exciton binding energy, and then we need to multiply basically by the area of exciton. So the smaller the, so it's proportional to the Bohr radius. The smaller is the Bohr radius, the weaker is the interaction, the weaker is the exchange interaction. The resonant Auger process is as follows. You have the band, you have one conduction band, and here you have another conduction band. Actually, they have a bit of peculiar dispersion. And this band gap and that band gaps are about the same. And then if you have two excitons like this, one recombines, and here the electron goes up. And then our estimates show that it gives reasonable value of Auger coefficient. You can check it. I do not have such slide, but you can check it just looking at the intensity as a function of exciton density. You can see that indeed there is a nonlinear decay according to this law. And then you can describe it within this simple model. These are the lines for different types of the sample. And actually there are no fit parameters in this situation. So we know the diffusion coefficient, the real one from low excitation power experiments, and we know the Auger coefficient, this Ra, from just measurements of photoluminescence integrated in the space photoluminescence. And you can indeed make some analytical theory, you can make numerics. I don't want to go into any detail. I want just to show you that even in this first simplest possible approach, you can get something interesting in these materials. And then again, if you go to higher densities, then the sample gets overheated, and then we believe that Von Wind and Zilli leads to formation of these halos. Now I stopped speaking about nonlinear diffusion effects. So this was just a kind of teaser. Something interesting happens. Now we will go to talk about, I would say, at least at first, less fancy. What are the physical mechanisms beyond these diffusion coefficients? What makes excitons propagate? And the main part of my talk will be about non-classical exciton transport, actually about exciton relocalization effect. And here I will show you some results obtained together with a group of Alexei Chernikov, experimental group, and we also collaborated with Ermin Malic group in Göteborg and then in Marburg. They did some very nice simulations within the Boltzmann equation to study all the details of classical exciton transport. So let me start with something very simple. I understand that the audience is different here, and I apologize for all these more or less trivialities for the members of Abrikosov Center who are online, but still I want to speak about some basics, and actually we are going to speak about basic questions about the mechanisms beyond the diffusion coefficient. So what people typically discuss. One option, it is well known, for instance, for organic semiconductors or for low quality inorganic semiconductors. There are some disorders. Excitons are localized in this disorder and eventually hop between different localization sites, emitting or absorbing phonons. So this is kind of phone hopping transport. In this case, diffusion coefficient, for instance, should demonstrate very strong temperature dependence, because hopping probability is exponentially dependent on it. And also there is in fact spread of diffusion coefficient, so one can expect that this diffusive behavior may be actually different, may deviate from standard diffusion law. There is another option, is that excitons more or less freely propagate in the plane, and then sometimes they scatter off disorder, or they scatter off phonons, maybe some other defects. Actually, my claim is the following. In high quality transition metallurgical coordinate model layers, the exciton transport, the exciton propagation is almost free. So excitons indeed propagate for some distance away and only rarely scatter. From experimental point of view, I will try to show you the results in a few slides. It follows from the fact that there is no extra strong temperature dependence of diffusion coefficient, and more or less diffusion coefficient, as I will show you, drops with increasing the temperature. So it contradicts with the hopping. And we probably understand why. So what we start our analysis with is the simple description of diffusion in terms of Boltzmann equation, quasi-classical propagation. We assume that exciton in free path is much larger than the exciton de Broglie wavelength. So exciton indeed propagates for quite some distance before it scatters. And then one can readily estimate the diffusion coefficient using this formula. You need to take squared velocity, thermal velocity of excitons, multiply it by the scattering time and divide it by 2. So you can arrive to this equation from different kinds of analysis. Basically, it just shows you that exciton propagates for the mean free path L during the time tau, and then the direction of propagation changes randomly. For thermalized excitons, and we know from other experiments that it is indeed the case, the transport takes place on longer time scale compared to the energy relaxation. You can replace V squared by the temperature divided by the exciton effective mass. And using the condition above, assuming that, okay, excitons are indeed free to propagate, then you have this standard criterion for applicability of this quasi-classical description of applicability of kinetic equation. We understand immediately that this should work if exciton diffusion coefficient would be much larger than the Planck's constant divided by the exciton mass. And if you put some parameters in the system, the mass is about the mass of the free electron, then the diffusion coefficient could be something like 1 centimeter squared. So if your diffusion coefficient is much larger, then that's okay, then this model should work. If the diffusion coefficient is much smaller, then excitons should be localized, there should be some point. Actually, it turns out that we are in kind of intermediate region. If we just consider very basic scattering mechanism, excitons interact with long wavelength longitudinal acoustic phonons in the sample. The scattering time is inversely proportional to the temperature. It can be readily evaluated again by the material parameters, by density of the materials and this deformation potential. Then what happens? The higher the temperature, the more phonons you have, and then temperature gets cancelled in this expression. the diffusion coefficient doesn't depend on the temperature, and depending on the material parameters, so for different transition metal dipalcogenide, it can be a bit different. It depends also on if you make estimations of on some band structure details, but it should be somewhere in the range of 1 several centimeters squared per second. So what we can see that we are in fact on the borderline of the application of the applicability of quasi-classical transport. And in fact, if you look at the experiment, for instance, at 4 Kelvin, you can get a value of diffusion coefficient rather close to these crude estimates. So on one hand, everything looks reasonable, okay? But on the other hand, you can see that, strictly speaking, this condition is not fulfilled. So one can expect some other effects to occur. One can expect some interesting physics to arise. And
Misha, where is the Exciton radiative lifetime in this slide? Tau is not the radiative lifetime.
It's assumed to be infinity. It is assumed to be very long. As I mentioned, answering to the question of Alexei, in fact, even especially at low temperatures, most of the excitons are dark. They are either in spin forbidden states, which are basically below in energy, or they are in the intervalley states, and they also have quite long lifetimes. So typically, I think that in these conditions, lifetimes could be on the order of several hundreds of picoseconds. This is the time during which the decay of photoluminescence occurs.
Misha, I also have a question. So in one of your previous presentations, I believe, if I remember correctly, you argued that the coherence is somehow preserved by this.
I will speak about it, Alexei.
Okay, because so my question is, what makes us sure that really phonon scattering is the dominating mechanism?
I will show. I will try to show it. I just want to go step by step. I want to reveal some parts of the puzzle. We do not have answers to all the questions, but at least I want to tell you that we try to understand some parts of it. So numbers are reasonable, but strictly speaking, from the viewpoint of the theory, we are in a borderline case. So what we can try to do, we can try to evaluate, as people usually do in the electronic systems, the lowest order quantum corrections to this classical quantity. So it should be exciton weak localization with the following specifics. The specific is that the scattering occurs not by static impurities, like it typically happens in the electronic systems, but by the long wavelength acoustic photons. And I will try to argue that indeed it is experimentally relevant situation, and just wait a little bit. But now I will show some theoretical slides. Again, everything is very simple. I want to remind you how in this semi-classical picture, quantum effects may appear. So exciton could go from the point A to point B. And in classical language, you have, of course, different trajectories, like this one, like that one. And then classical language, you can say that all these trajectories are more or less independent. You need to calculate the total probability just by summing the probabilities of realization of each trajectories. In quantum mechanics, it is not the case. You need to sum the amplitudes of probabilities, as it is shown here, and then you need to take the absolute value squared. While it is not so easy to calculate this sum, one can make very simple argument that actually, usually, quasi-classical description should work nicely. The amplitude of probability, is just its absolute value and some phase. And the phase is related simply by the fact that once exciton or any quasi-particle propagates with a given wave vector, then the phase is just the integral of the wave vector, which changes, of course, as a function of time, times the element of its path. So in relatively clean system, or if the scattering is not that efficient, we know that we have this condition. The mean free path is much larger than the wavelength. We take two different trajectories. These trajectories differ at length by at least by one mean free path. So the difference of the phases is the product of exciton wave vector times mean free path. In fact, it is much larger for typical trajectory. But this parameter, in theory, is already very large. So it looks as if you can safely neglect all quantum effects, and indeed you can say that once excitons go from A to B, then you should simply sum up classical probabilities. And if you do so, you of course obtain this value for the diffusion coefficient, and you actually just get the diffusion law. There are, however, special trajectories where this condition of vanishing interference is not fulfilled. Let us assume that we have a trajectory evolved with a kind of self-intersection, as it is shown here. Then exciton can go with clockwise or counterclockwise. These two paths, from the classical point of view, are completely equivalent. In terms of interference, the phases for clockwise and counterclockwise propagations are also exactly the same, because these two trajectories, of course, if the scattering were exactly the same conditions, they are just related by the time reversal, so you change the direction of momentum, and since you propagate backwards, you also change the direction of this dA. So the phases are the same. You have perfect interference at such trajectories, clockwise and counterclockwise. So this kind of trajectories works, you may say, like cavities. The excitons start to get localized at these trajectories. You have constructive interference, you have localization. We know what it is from physics of electronic systems, and I think that the great contribution to the field was done by one of our board members, by Boris Altshuler. We know that it's a sort of precursor of strong Anderson localization, then the disorder becomes stronger. But here, and coming back to the question of Alexei, we need to answer the question, actually, how well this equivalence of the phases is preserved if you have scattering by acoustic phonons. Because you may say that, okay, it works nicely for impurities. The disorder is static, everything is static, phases are just these geometrical phases. But phonons, they bring or remove some energy, and that is why something may change. We were very lucky that people have analyzed this question, at least partially. In fact, if you study scattering of two-dimensional exciton by acoustic phonons with long wavelengths, so with small momentum, then this scattering is quasi-elastic. The speed of sound is much smaller than typical speeds of exciton propagation. And in very simple language, you may say the following: acoustic phonons just make some random potential for excitons. This potential, of course, slowly changes with time just because phonons propagate. But this change of potential with time is not too strong. You can quantify the characteristic energy transferred in the process of emission or absorption of a phonon is the square root of the exciton kinetic energy and some characteristic phonon energy, exciton mass, multiplied by the speed of sound squared. And this quantity is small compared to the kinetic energy of exciton. It means that actually exciton loses or gains energy in small portions. It is what is known as quasi-elasticity. And if you look at the behavior of energy as a function of time, then you can observe a diffusion, but now in the energy space. And it is quite typical for quasi-elastic process. The energy relaxation time can be defined from the condition that the change of exciton energy is on the order of its mean energy, on the order of temperature. And this time tau epsilon is quite long. It is much longer than the momentum relaxation. But this time has nothing to do with breaking of the phase coherence. In fact, the phase coherence is preserved at the time scale tau phi, where the change of exciton energy is on the order of energy uncertainty related to this time tau phi. I will give you more precise, more accurate calculation of this dephasing time probably on the next slide, but physically, these arguments, I believe, were very clearly formulated in one of the papers by Altshuler, Aronov, and Khmelnytsky 40 years ago. And then what happens? You have this dephasing time. It can be evaluated through the parameters of the system. And the ratio of dephasing time to the momentum scattering time scales as temperature to the power of 1/3. it increases with temperature, not very fast, but still it increases with temperature. Physics quite clear. The higher the temperature is, the larger is the exciton energy, and the smaller is the ratio between the exciton energy and the energy transferred in each scattering act. The collisions become more and more quasi-elastic. And then what we can expect? You can expect that in the case of exciton scattering by acoustic phonons, at least in some temperature range, quantum effects should get stronger with increasing the temperature. The phase coherence should be preserved longer and longer. You can calculate, I won't go maybe into much detail here, you can calculate it in different fashion with the same result. You can calculate the interference amplitude, Couperon. You can assume that excitons are indeed in some moving disorder. You can take into account explicitly the elasticity of the scattering. All this brings to the same result. The correction to the diffusion coefficient delta D is given here. It is given by some prefactor, which is in our case on the order of unity, and this logarithm. Sorry? Of the phase relaxation time divided by the momentum relaxation time. And this logarithm increases with increasing the temperature. Then what you can expect? You can expect that the diffusion coefficient, total diffusion coefficient, will drop with increase of the temperature. Of course, at some point, actually at temperature of about 50 Kelvin, other scattering processes will start to play a role. You do not have only long wavelength acoustic phonons, but you have zone age acoustic phonons in these materials with relatively low frequencies. Optical phonons start to play a role. And if you just take roughly into account, then the correction to the diffusion coefficient should behave like this. First, you should have a drop of diffusion coefficient up to, I don't know, something like 30, 40, 50 Kelvin, and then a kind of increase in diffusion coefficient back to the classical value. On the other hand, the classical value of diffusion coefficient is expected to be temperature independent. And now we can test these predictions comparing with experiment. I will skip these details and we analyze different scattering mechanisms. It is not very important. Now I'm going to show you some experimental results. So the experiments were exactly as I described before. Low excitation density to avoid any nonlinearities. Measurement of the diffusion coefficient from the expansion of exciton cloud. And red points are the diffusion coefficient in the range of from, I don't know, 4 Kelvin to about 45, 50 Kelvin, and it drops with the temperature. However, the question may be, okay, probably we just disregarded some important scattering mechanism. Probably simply this scattering time that enters the diffusion coefficient changes as a function of temperature, just decreases faster than the temperature. So then probably the effect should have purely classical explanation. Okay, what we can do experimentally? Not we, of course, our colleagues. They can measure the broadening of exciton resonance as a function of temperature. So in the same experiment, you just measure the spectral width of the exciton. And this broadening gives you relatively accurate estimate of the scattering time, of the scattering rate. These are the points. They are collected at the same sample from different excitonic states, low temperature, so you can resolve different excitonic states relatively clear. And if you remove the contribution due to inhomogeneous broadening, then you get very reasonable linear dependence, as it should be for acoustic phonon scattering, with very reasonable coefficient, which is close to theoretical prediction. And moreover, if you do this broadening, if you put it in the formula for diffusion coefficient, you will get these blue dots, which do not match the experiment. So you cannot explain it, at least in this simple language, by classical calculation. Our colleagues from Chalmers and then from Marburg University, Ermin Malic and his co-workers, actually did some more complicated modeling of exciton diffusion coefficient without quantum corrections, but taking into account the specifics of band structure and specifics of phonons. And actually, in the interesting temperature range, it is more or less constant. On the other hand, so yes, we can try to claim that this decay indeed comes from some unaccounted process, from interference of excitons from weak localization. On the other hand, I want to be honest with you, and this I always say at the conferences, and we clearly write it in our paper, that still we have a problem with the magnitude of the effect. So the prediction for the parameters we have is smaller. So you can probably change the diffusion coefficient by a factor of, I don't know, by 20%, 30%. In experiment, you can see that the drop is much more significant. So still starting from there. Yeah.
Maybe ask at this point. So anyway, there is an assumption that there is no, right? Then considering diffusion, okay, you argue that the temperature depends on the diffusion coefficient. That is, the experiment proves that this is a photon dominated process. But potentially, if you would have drift, you would maybe have the same phenomenology.
Maybe I do not fully understand your question. What do you mean by drift? You mean by the drift caused by exciton-exciton interaction?
Yeah, just the ballistic propagation of this cloud.
It's a good point, but I believe that experimentalists check very carefully that they work here at very low excitation densities, so typically less than 1 exciton per pulse, per optical pulse, and they do not see any change, any significant change. I don't know, more than by 5% of the diffusion coefficient in this temperature range, with changing the power, I don't know, within several times.
I see. Okay, this, but also there is another question about the role of spin in this story. There is definitely some spin diffusion, spin relaxation.
Very good question. Thank you, Alexei. You haven't addressed the view about this question before. So, in classical language, spin plays almost no role in this situation. Of course, you have longitudinal and transverse excitonic branches split by the long-range exchange interaction. If we speak about bright excitons, it gives you some renormalization of effective masses, but it is not too strong, and in principle, it shouldn't affect much the diffusion coefficient. Importantly, spin or pseudo-spin of excitons can affect the interference, similarly to the case of electrons. The situation is, however, a bit different. Electrons are fermions, and for closed trajectories, if the spin-orbit interaction is present, the Berry phase is pi, and that is why you change from weak localization to weak anti-localization. That's a very strong signature of spin-orbit interaction. And you can observe it in many cases. You can evaluate Rashbo-Dresselhaus terms in this way. So for excitons, they are bosons. Actually, the Berry phase in this particular situation is 2 pi. It doesn't mean that spin doesn't affect the interference. It affects the prefactor by about a factor of 2 in the best case. But at least if you study the diffusion of overly unpolarized particles, again, it will not change you dramatically the regime of transport. It will still be weak localization. This we have analyzed a little bit, and we do not see a way how including spin may strongly change this result.
Can I ask also?
Yes, Misha, of course.
I mean, these are wonderful, clean structures, dream of all experimentalists. But is there any regime when the main mechanism of propagation is kind of photon recycling? That you kind of only can propagate by recombination and exciting in some other localized position, or maybe it is in more superlatives where you have this Hobbes rare, or is there any, because you know you are doing wonderful job, but it is in some sense similar to the weak localization theory for charged particles, and I want something which is purely excitonic.
Yes, so it's a very good question. I just want to
maybe I missed something. I don't know.
I can tell you. In fact, you can make bad sample. I think for experimentalists it is even easier. So our colleagues in Moscow, in Lebedev Physical Institute, have samples of molybdenum deselenide or desulfide, I have forgotten, which were not made by the Scotch tape technique, but which were grown using kind of CVD procedure. These samples are very defective. And in this case, you observe exciton hopping for sure. And
I mean, hopping means kind of physical hopping, or is it
This we do not-
recombination and reabsorption in different places? What
This-
do you mean by exciton hopping?
this we do not know so far, but we have signatures in these bad samples. Unfortunately, I don't have any figure about it, but we have signatures of two things. First, excitons are strongly localized, and they somehow jump from one localization site to another. Maybe the photons due to this first
Reabsorption mechanism. Yeah, photon recycling, whatever you call it.
Yes, this is for sure. And then in these very samples, you also see some strong deviations of diffusion from normal one. So you can have at some regime a kind of sublinear expansion, which may be an indication that you have a rather strong spread of the hopping times. We have analyzed it a little bit. Maybe there will be some more data and some more room for the theory, but in principle, you are right. There could be some dirty cases, also very interesting.
Okay.
Alexei, may I ask you how much time do I have?
Oh, you have plenty of time. We are so few with them.
Okay.
I mean, that plenty of time is 10 minutes.
Yeah, exactly. Okay, so then probably I will just speak about other story, also a bit theoretical, and also with some experimental realization, and then I will conclude. So this is the story about exciton transport again, but in the presence of precarriers. So in these 2D semiconductors, you can relatively easily dot them. You can add more electrons to holes just by using electrodes. And in this case, your sample acts as a plate of the plane capacitor. So it is very convenient tool for experimentalists. Another note, you can change not the temperature, not the excitonic density, but you can change the density of electrons. And then from basic semiconductor physics, from physics of semiconductor quantum wells, we know that what in principle happens is the following. Exciton can pick an electron from the Fermi sea and form a bound state, a triangle. And then you end up with new quasi-particles, triangles, which have their own life. However, in conventional quantum wells, the situation is as follows. The exciton binding energy is about 10 milli-electron volts. There could be deviations, could be smaller, could be larger, but something like this. The trion binding energy is 1, 2, 3, 4 milli-electron volts. And this is more or less the scale of disorder in the system. And that is why what happens? If you have just a few electrons in the system, then the Fermi energy is smaller than the trion binding energy. Then the trions are more or less stable, but everything is localized by the disorder. If you add more electrons, then Fermi energy becomes larger than the trion binding energy, and trions vanish. Actually, excitons will vanish as well due to the screening and mode transition and so on. Here, exciton binding energy is huge, hundreds of milli-electron volts. Trion binding energy is also large, 20 milli-electron volts, and the scale of disorder is something like 1 milli-electron. So you can easily tune here, you can easily study physics of trions, you can easily study effects that may not be related only to the formation of these bound localized three-particle complexes. So our question, the colleagues from Dresden, was what happens with the transport, how to describe diffusion in this kind of Bose-Fermi mixtures. You have both the exciton and you have electrons around the fermions. And in this case, it turns out that the most convenient way is to use so-called Fermi-Polaron formalism. It's an approximate but very convenient method to take into account many-body nature of everything. Because in fact, if you have a Fermi sea and if you assume that your electrons are not localized, then your exciton can pick this electron or that electron or that electron. So you cannot really speak in terms of three-particle complexes. So then the problem is solved like this. You assume that the exciton binding energy is indeed very large. And then you consider exciton just like a robust particle with no internal structure. These excitons interact with electrons And this interaction is more or less attractive interaction. You can form a bound state. You can describe it within the scattering theory. And for instance, you can get a very simple in 2 dimensions, very simple relation between the matrix element of the interaction and trine binding energy just from studying the scattering matrix, the T matrix of exciton and electron. And the trines, you can say, formally appear here as a poles of this scattering matrix. This is how you solve the 3-body problem. In fact, you can do much better. You can make variational or just brute force calculation of 3-particle bound state. But then what we need is just the binding parameter, and it gives you simple relation with the interaction parameter. And now, once you know the scattering matrix, then you can take into account the fact that you have a Fermi C, so you do not have just one electron, but many of them. And then you calculate the renormalized exciton green function. You simply say that in any optical experiment, you first excite electron hole pair, the exciton. And then this exciton, okay, it interacts with electrons. We need to take this T matrix, we need to do all the standard stuff. And then people speak about Fermi polarions. They, in fact, what you can interpret them in the following way. You excite eventually trine, a 3-particle complex, but once you remove the electron from the Fermi C to form a trine, a 3-body bound state, then there is a hole in the Fermi C, which knows a little bit about correlation in this trine. And then you have, you may say, even a 4-body excitation. Hole in the valence band, 2 electrons in conduction band, and 1 hole in the Fermi C. It was actually, I think that not only in condensed matter, but also in atomic physics, it was Robert Arnoldovich Suris who first paid attention to this point. But then there was a very big activity on what people call Fermi polarions in physics of cold atoms. And now there are a lot of discussions what will be the most appropriate way to deal with trines and Fermi polarions in 2D materials. Anyway, this model is very convenient. It provides reasonable agreement with experiments. In some cases, you can simply merge the approaches of trines and Fermi polarions. I'm just going to show you the result. High quality sample, if I'm not mistaken, tungsten diselenide, encapsulated by hexagonal boron nitride, gate tunable. You have exciton bright somewhere here, the simply cut off. And then you have positively charged trine or negatively charged trine with this specific cubic structure, some replicas of these states, and so on. So lines are very narrow. You can easily change the density. You can go to the p-type regime, n-type regime, whatever. And you can again measure the diffusion with exactly the same procedure I have explained. And this is the diffusion coefficient here on the right as a function of precarrier density. So red points here, they show the p-dot region, blue points show the n-dot region. What is striking is that the diffusion coefficient first rapidly drops and then even increases. And then, of course, it slowly drops for higher density.
Misha,
yes.
Maybe before we go to ground, may I ask you
yes.
a general question? So, what I remember from Suris works on a quark is that okay, you can take an electron from below the Fermi level, put it above the Fermi level, you have an electron full, and you associate an exciton with them, and it was then experimentally studied by Glazov. That's all right. But before that, in 90s or even 80s, there was also a work, I remember work of Picus Jr., but maybe there were others. And there the argument was that, okay, you optically excite an exciton, but part of your conduction band is occupied, so you can only use the states that are unoccupied to construct your electronic. And also for the extra electron that connects to that exciton, you can take use those states that are occupied.
Yes.
So that gives some restriction, etc. So are these two very different quasi-particles, or just two different views on the same phenomenon?
More or less, these are different approaches to the same phenomenon from different sides. So the old work of Fyodor Picus, and I think that there were a lot of papers about the same time, were more or less about the mode transition for exciton. You have, rather than Fermi C, the Fermi energy is much larger than the trine binding energy, so you can forget about three particle correlations, and then you indeed need to make your exciton orthogonal to the Fermi C. And in this case, you know, the binding energy of exciton vanishes, thus the latest strength vanishes, and then at some point the exciton dissociates. And then you have this Mahan singularity, which is probably not very easy to observe. Here, the regime studied by Suris and in the physics of Fermi polarons is different regime. Here, the Fermi energy is much smaller than the exciton binding energy, and it is typically not too large compared to the trine binding energy. And then you can present the state, the many-body state of your system in the following way. Exciton, so zero here is vacuum, meaning the Fermi, when you have occupied Fermi C. So exciton and unperturbed Fermi C plus exciton in some other state and excitation in the Fermi C. You pick up electron from below the Fermi level and you have a hole there. In fact, if you look at this three-particle correlation, exciton plus electron, its wave function is the one we described the trine. But you have this Fermi C hole, and this was the idea of Suris, of course. And then you can also interpret in terms of quadrons and speak about their fine structure. But basically, if you do this approach, at least in very simple condition, you recover all the physics of Fermi polarons. And at low density, the Fermi energy is much smaller than the trine binding energy, then typically this Fermi C hole plays no role, and you may speak about trines. You can reproduce the same results. So these are two approaches from different density regimes.
I see. But the important thing is that even if you have the shallow Fermi C, then to find this extra electron to form your trine, you can only rely on the state that are.
Exactly, and in this trine, the electron should be in the empty state. Therefore, in this equation for the T matrix, we have this factor 1 minus n, meaning that Pauli principle works. And here, then I calculate the exciton self energy. I actually integrate over only occupied states, calculating this loop, and therefore I have here the factor proportional to the electron density, and it gives you basically the proper transfer of those latest strengths between the ground exciton state and the trine, which is proportional to the exciton, to the electron density, and there's another factor can be converted to the trine radius squared.
But sorry for
Okay, but
that's interesting. I'm just trying to understand. So if we have a shallow C, this hole that remains, it may only have a relatively low wave vector, so it is quite delocalized. And probably that is why it is not.
Exactly. Yes, physics, exactly. And then it plays no role. If you calculate all the matrix elements, you do not need to think about all the details. What you need to do, just properly count the field states in the Fermi C, or properly count the possible states for the hole, and then you arrive to this exciton density factor. If Fermi energy becomes comparable to the trine binding energy, then the situation becomes more complicated. Misha, you have a question? Yes.
Yeah. Since you already done this kind of weak excess of particles, or weak Fermi level case, can you comment like on the binding energy of the main exciton? Is it influenced by that screening by the free carriers? Because it's known that in 3D, for example, the line becomes weaker, but because of the competition between band gap renormalization and screening, the exciton energy stays approximately the same. Does exciton energy changes noticeably with this concentration of free carriers?
Very good question, Misha. Thank you. So theoretical estimates, we haven't done this, but what I have learned from the literature, there are a lot of people doing this for 2D materials, and of course, you know, all this works for quantum wells. back in, I don't know, 1990s, 1980s. And
I was just asking an application to
Yes.
dehalcogenase.
So basically, it is more or less the same as in bulk systems. There is significant cancellation between the band gap renormalization and the variation of exciton binding energy. So if you look at the spectrum, of course, you can see that exciton line, if you change the doping, it shifts, and you have something which you can either ascribe to the variation of the prime binding energy or to what people call this Fermi polaron shift. But in fact, if you, even from this data, if you try to evaluate the exciton binding energy, say by looking at the distance between X0 and the excited state, 2s exciton, then the binding energy wouldn't change much.
But if there is that shift, which is quite prominent at the bottom, do people use kind of, that means that you can move, excitons will move to the area where the binding energy is bigger, yes, or whatever, trions. Can you do local gating and make the drift on top of your diffusion?
People try to do this. So far, I think that there are some technical problems. Of course, people tried even the following. They use this monolayer and then they put a bit of graphene on top. And it changes already the profile of bands and even slightly changes the binding energy. In principle, it should be sufficient for excitons to go beyond this graphene. But the main effect there is just that there is an additional channel of non-radiative recombination. Electrons and holes go to this graphene and combine. But this idea is very good and people are trying.
Okay.
Okay.
Actually, I found something, but
okay, that's
never mind.
very interesting.
There is electrical tuning, but it is for bilayer.
For bilayers, there is a very interesting way. Indeed, you can use the inhomogeneous electric field to exciton.
That was more or less related, but it is bilayer is different.
Yeah. So last point. So this rapid drop of the diffusion coefficient we observe here is in the regime the excitons mainly scatter the free electrons. You have more electrons, you have more efficient scattering, you can derive the expression for the experimentally relevant parameters. It is more or less consistent also with the line width broadening, and then you get significant decrease of the diffusion coefficient. And we know that in this particular regime, weak localization plays no role. This scattering is sufficiently inelastic. For trions, since they are already bound for Fermi polarons, already the main effects of interaction with resident electrons are included. And that is why within the same model and also in agreement with experiment, the scattering rate for trions is density independent. And then it actually demonstrates this behavior. You at some point switch from excitons to trions, and then the diffusion coefficient even increases, and then it weakly decreases because there are effects which are beyond this model. So you can see very clear signatures between the change of regime of propagation, say from the scattering regime to the quasi-particle regime in this Bose-Fermi mixture. And basically that's all. I probably skip all this. And I want to say that these two-dimensional materials could be a very good systems to bridge optics and transport. You can observe optically transport phenomena. You probably can have an access not only to nonlinear transport, but to possible signatures of quantum effects and to scattering in Bose-Fermi mixtures. And also, I didn't tell you about it, but there is a big activity related to the spin or Welle transport of quasi-particles, spin and Welle Hall effects and other things. But there are a lot of room to study, and I hope that someone else will tell you about it. So thank you.
Thank you very much. So any questions on Zoom?
Okay, maybe I will ask. I'm sorry, it's Boris Altshuler speaking.
Yes, Boris, please.
Maybe I had missed it, but if you are speaking about effects of applied voltage on all these measurements? Can you just create some current of free carriers and see its influence on the optics?
Yes, it's a good point. So people now try to do this. People try to apply currents, and then they speak about either transport of trions, or they speak about optical dragging or current-induced, electron-induced dragging of excitons or Fermi polarons. There are even some experiments and models about it. In my view, there are still a lot of things to do, and I'm not sure that all these theoretical descriptions are very correct. But yes, these ideas are good, and people try to explore them.
Okay, thank you.
Thank you.
More questions? What else?
Vanik, I asked many. Vanik, I would let.
Yeah, thank you very much, Misha, for the talk. My question is kind of related. Maybe it's a little bit naive, but when talking about a trion transport, can we really say there is a physical motion of the charge? Can we talk about electric conductivity in that case?
I think no, in the following sense. So typically, as I have tried to show here, typically under conditions of optical excitation, you do not have charged complexes. You create exciton, and even this guy is also neutral because you have electron in the Fermi and also a hole in the Fermi. So the system is on average neutral. However, if you apply electric voltage, you can drive electric current for electrons in the system. So then you change this distribution of electrons, this ground state of the electrons. And then this electric current can somehow interact with excitons. So moving electrons can start to push excitons and make them move. And also these moving electrons in principle can start to push Fermi polarons or trions and make them move. So there are some models about it. There was very comprehensive paper by Richard Schmidt, Ataka Mamoglu, and co-workers about optical transport of neutral excitation, something like that. But still, again, I think that there are a lot of additional effects to study.
Okay, thanks.
More questions?
Yeah, I wanted to ask. Your two-dimensional excitons, they are known to be very sensitive to the dielectric background.
Yeah.
Are there, I mean, for sure, there are, I think I know some work on kind of funneling when you do gradient of dielectric constant, but are there natural, I mean, light-induced gradients of dielectric constants which make them go further or stay localized to counteract simple diffusion? Is there anything like that?
I do not know. Maybe there could be some mechanisms, but I just do not know about this.
Because we know that you know, dielectric
Yes.
constant enters even you know, quite prominently.
Yes, so what people know for sure that actually the main contribution to inhomogeneous broadening in this system is related with the so-called dielectric disorder. Just because of fluctations of these HBN layers, you have fluctuations of Rydov-Keldysh potential. So it is kind of,
that's what I'm talking about. Yeah,
it induces you a kind of inhomogeneous broadening. It is more or less established, I believe, both experimentally and theoretically.
More questions? Okay, probably it's
I do not see.
if it is not the case, so let me thank the speaker again very much.
Thank you.
And so we carry on with our seminars. Next week on Wednesday at 11, we'll have most likely the talk by Andrei Turlapov. It is yet to be confirmed, but definitely we will have a talk. So please don't miss the announcements and join physically or virtually. Thank you for attending this today.
Thank you. So
Thanks,
I can,
yes,
goodbye. I can probably disconnect. That's it.